Everyone here. So yeah, Robert already said many exciting things about Ray and Anyscale. So I'll just fill in more technical details of how Ray enables these different applications, enable large language models and generative AI. And brief introduction, my name is Zhang. I'm the head of open source engineering here. So basically, I lead the open source Ray team. So if you're interested in open source collaboration, please reach out to me. Email, Twitter, either works. Yeah, so let's get started. This is a quick summary and structure of the talk. First, some technical details about Ray and Anyscale, pretty much a follow-on from what Robert said, and then I'll talk about how we see most companies are using large language model now and our prediction. And then I'll go into the technical challenges surfaced from these use cases, and we'll talk about how Ray is a critical part of the solution. So I think, Robert already introduced a lot of concrete use cases. Here, I'll just really quickly tell you how, like, under the hood, how does it work? Ray itself is a complex piece of software, so I'll just go to very simple examples. So TLDR, Ray distributes any arbitrary Python code, right? Here I have the most simple example. So you have some Python functions, you have some Python classes. So what happens if you want to run this Python code on a cluster of hundreds of thousands of nodes? So all you need to do is to decorate these Python functions and classes with this very simple one line at read-out-remote. And then they become a unit that you can schedule to the cluster. And when calling them, you use the .remote keyword, and then you can add like different functions calling into each other. At the end, you code read.get, and here this call will block until you get the result. And later I'll introduce some concrete execution graph to help you better understand. Right. Similarly, for a class example, right, we have a simple class called counter. It maintains one simple internal attribute called value. Every time you can increment the value, this is a basic unit of stateful computation, where you can maintain certain states. So similarly, just decorate the class at read-out-remote, and then you can trigger the class anywhere on the cluster. And here is a simple illustration on a cluster of 2 nodes with this example, right? We define a function called read-array, basically take a file, return ND array. And the function can be run on 2 nodes, each having a file, right? So when executing this line, what actually happens is that we trigger an asynchronous computation. And then secondly, we trigger the computation for ID true, and we start constructing this dynamic task graph. We build a task graph at runtime, and the only time we actually trigger this computation is at this blocking call called read.get. So by doing that, you can launch arbitrary number of tasks, actors, parallel on the cluster to fully utilize the compute resources. Another beauty of Ray is easy specification and easy access to different kind of hardware. Right here, I'm illustrating this by the example in the class, in the counter class. You remember we defined. You can easily define for this particular class and the same for each particular function, how many GPUs, how many CPUs you want. This has become like increasingly critical for the large language model, generative AI, or just an arbitrary machine learning pipeline involving different kind of computation. And what I have not shown in this example is that you can go even more advanced. You can do fractional GPUs, right? If you anticipate your, for example, model training or inference will occupy only like half a GPU, you can like specify, oh, this class take half GPU, another take another half GPU. As GPU are getting harder and harder to get and more and more expensive, we think this will be a killer feature for people's performance and productivity. And at the end, I'll leave time for any questions about the technical details. All right. Now going into the part of how Ray and Anyscale help solve the challenges of large language models. So first, we first look at the status quo, right? How people are using large language models. So our observation is that there are 2 kind of cohorts. One is directly calling these hosted APIs, right? So Most well-known examples, OpenAI, right? Many people use ChatGPT, or if you're lucky, you can use GPT-4. But basically, the model is hosted by OpenAI. You just directly call the API. It's more in a black box fashion. Similarly, for Cohere, for Anthropic, and Hugging Face, they have their own version of APIs you can call. It sounds very simple, right? It's just one URL you can hit and get the result, string in, string out. But actually, it's more complicated than that. So building a large language model based application have multiple stages, right? You need to generate your prompt, and then you generate the response. And you use the response to actually, you need to actually moderate the response and then build your application. So if you think about this pipeline, then there are multiple interesting challenges or issues. The first one, which many of us feel, is the cost. Here's a table of doing model training and inference on different kind of models. You can observe that it's kind of high. So a few interesting observations. Actually, the cost of deploying the model and calling the API is actually sometimes more expensive than training the model, right? And how about more specifically about the deployment? There are some concrete numbers, but TLDR is that if you're doing a real conversation with like 10, 20 exchanges, it can easily go up to like $1, $2. This is it's much higher if you think about the experience, for example, doing Google search and like similar previous generation interactions. So cost is a big challenge. What's the next one? So some more details, right? Note that this cost is with both fine-tuning and inference. Fine-tuning is more of a one-time capital expenditure, CapEx. And inference is repeating, like every query, you incur the cost of inference. But cost is not the only issue. Latency is also getting an important issue. Actually, latency both is increasing for these APIs, and actually it's getting unpredictable. You can never anticipate the latency you will get when using these hosted APIs. Right, it can easily go to multiple seconds, or in this example, over 30 seconds. You can hardly call this a real-time kind of interaction. So this is actually compounded if you do inference across multiple costs. You chain the different costs, which is becoming an interesting scenario, right? People check one source and like fact check with another source, combine their strings. This latency can easily build up. And if you cross multiple companies and domains, right, you do one Cohere, one OpenAI, that's like getting things exponentially more complicated. So yeah, then is the even more tricky challenge of in the general domain of security and privacy, right? So after all, in fine-tuning, you're providing your data to the whoever building the model in a black box. And even in doing reference, you're providing your prompt to whoever hosting the model in a black box fashion, right? So there are a lot of recent research about the security vulnerabilities, right? So by providing the data, even by looking at the model, some data can be kind of inferred. So for these reasons, so in conclusion, yes, many use cases you can do with the hosted API model, but many other use cases are not really well suited. The key reasons: cost, latency, and data security and privacy. So because of these reasons, right, so the users, they see these concerns, so there's actually another cohort doing what we call the in-house large language models. So this is definitely a very early trend, and from our signals of the users, this landscape is definitely still evolving. The entire ecosystem is evolving, and actually we would say it's not really ready for prime time for most companies. Right, so here, next, I'll give more details of how people are using these in-house large language models. So basically, it involves these different steps, right? You download your models from Hugging Face, where Hugging Face is like a popular place where people download these models. So as far as I know, the most popular ones, like GPT-J, is like 6 billion parameters. The model size is like 10, 12 gigabytes, can fit in one single GPU, kind of is many people's starting point. And there are more and more coming up, like Dolly from Databricks, and there's a new model from UC Berkeley. You download the model, and what you do, sometimes people fine-tune the model with their own data. For example, you download GPT-J, you fine-tune it with Winston Churchill or Shakespeare's. You can suddenly talk as Shakespeare's. And then what you do, you serve these models, right? So then seemingly you're addressing many of the challenges I mentioned before. The cost is lower because most likely you're using either one GPU node or a small number of GPU nodes where you can control the cost. And latency is up to your control, and you don't worry about data security and privacy. Right. But what are the pain points of doing this, right? So one is actually scaling is becoming hard to manage, and scaling is costly. Right. That's why I mentioned like single node GPT-J is many people's starting point. But if you think about like why ChatGPT really impressed people is the amazing model performance. And although there are many, it's an evolving field to correlate the model size and performance, but directionally we all know that the larger the model is, the better result it can deliver. Right, so people usually start using the smallest single node model, but they have the need to scale up. And then they have some concrete technical requirements, right? Need to support the spot instance. Otherwise, the cost will just increase very quickly. And they want to run distributed workloads. What if I want to fine-tune the model on a larger data set, for example, the entire Wikipedia or your open source documentation site, right? So then you do need like data parallel training. And it's hard to get expensive GPUs. If you go to Amazon and good luck getting A100 and right, so it's even you have money, it's sometimes hard to get hold of the expensive GPUs. So the second challenge is that the existing technical solutions for serving and inference do not really work that well. So one is how to handle replicas, right? So when we're talking about inference, then naturally you need to handle like multiple parallel incoming requests, like on a per second basis. How do you design the mechanism to spin up multiple replicas so they can respond to like different queries, right? And also you need to integrate the response into your business logics. Many times people want a different experience based on the responses from large language models. So existing solutions are not, based on our understanding, not flexible enough to support these two requirements. And then, yeah, training on the training side. Training is also unstable and hard to get working based on current solutions. One is that when doing fine-tuning, naturally you need to do auto-ML, right? Tuning the hyperparameters. This is a key thing of increasing the productivity, and this is not working well yet with large language models. And also, people commonly find a lack of a platform where they can iterate really quickly and scale, because this is a very early, very nuanced domain. People really need to try different things and select the best and go forward. So the TLDR is of how Ray meets this challenge. Again, I want to talk about the three aspects, right? So we believe Ray provides the answer to the questions, the three questions. One is simplify the orchestration and scaling. I think this is where, if you like, you can try to remember the simple Python example I gave, right? The power in Ray is to spin up and orchestrate arbitrary Python code, right? This gives Ray the power to orchestrate this different kind of computation needed for this complex pipeline of really using large language models in your application. For example, spot instance. We support Ray supports spot instance for data parallel training. When spot instance is taken back by the cloud vendor, will just shrink the training size of the trial and easily spin up and run distributed workloads on any cloud, right? So because there's no lock-in, it's open source. And you can run, actually, another interesting point is that in addition to running on one single or a small number of expensive A100, now you can run on a larger number of cheap GPUs to achieve the same results. One is easier to get, and secondly, the total cost is lower. On the inference and serving side, so Ray can support actually connecting your inference logic with your business logic, right? because everything is basically function calls between different pieces of Python code, right? And then we support multi-node serving by spinning up multiple replicas and having the routing logic so that we can handle a high QPS. On the training side, right, so Ray comes with distributed data parallel training. So if you have a larger data set, you can, by using multiple nodes, you can basically speed up the training with a linear speed. Ray is very Python native. This is a key thing. I think Robert also mentioned many ML platform users, they adopt Ray because the kind of code people write on their laptop is very similar to the code running on the cluster. It's just a different number of nodes, right? So it's very easy to write a piece of code and push to the cluster. Yeah, so yeah, minimum code change to enable the actual training on a cluster on different clouds. So yeah, so in summary, right? So for this cohort of doing in-house large language models, what are we observing? We're seeing that there's definitely a strong need for something equivalent to the Linux LAMP model. I think depending on when you started doing tech, you might be more or less familiar with this. I should have like hidden the actual names and let people guess. Right. So yeah, Linux, Apache Server, MySQL, PHP. That's the. So before LAMP, I think people were having the challenge of lacking a standard stack, and now we're seeing the echo of that. Right. So in this nuanced space, people really desperately need a standard stack of like different layers. Oh, you do different computing using Ray. You do different things using different layers on top of it, so that people can innovate with the maximum leverage. Right, so and Ray, our observation is that Ray in this upcoming evolving standard stack, Ray is being used for GPU management and runtime orchestration, right? This is what, for example, OpenAI has been doing for their large model training, and many smaller companies are also doing. So, and also more detailed in second level details that we see two different tech stacks evolving. One is this ultra, very large, very high performance. You can even compare that with HPC, like supercomputers, MPI, that kind of stack. So really to push the boundary of model performance. Another is convenient and cheap. I'll introduce both in more details. So one is, yeah, just really pushing the boundary of state of the art. Here, one example is we just gave a joint talk with NVIDIA and Berkeley Alpa team about using this stack, right? NVIDIA as a hardware and JAX as a compilation layer, Ray as a GPU management and runtime orchestration, and Alpa to divide the model and tell you the best model sharding and parallelism mechanism, and then define the model, right? So this is the stack that we used to really push the boundary. When training this 175 billion parameter model, which really the state of the art, we exceeded the performance of all existing solutions. And here's the actual results if you're interested. So we compare the petaflops that you can achieve on different number of GPUs. Right, so some technical details, right? So how, like, what are the fundamental reasons to make this stack train state-of-the-art, like 175 billion models faster than existing solutions? One key piece is this project, open source project called Alpa, which is right now being managed by both Anyscale and Berkeley researchers. So what Alpa does is that, so fundamentally training and serving large models is a bunch of matrix operations, matrix multiplications. And the reason it's expensive is that the matrix are large and there are many steps in the computation compared with the previous machine learning paradigms. So what does Alpa do? Alpa just explores different ways of sharding the computation. Like one thing is to divide the compute graph, right? So for example, this part is one GPU node, this part is one GPU node. It can do multiple things. Another is to, within a single matrix multiplication, also shard that, to shard each individual matrix multiplication. It has more advanced sharding mechanisms. So I think that's one key piece, the sharding, and really helps to map each shard flexibly to the most suitable computational device. happy to share more details after the talk or via DM. So alternatively, like I previously briefly mentioned, this is the convenient and cheap stack. So what we see people do is like go to Hugging Face, download the model, use DeepSpeed to try to squeeze the model into a single GPU node, and use PyTorch for the training framework, and use Ray again for accessing the hardware and orchestrate, and run on different hardware. So yeah, here we have some concrete examples of using the most popular single node model called GPT-J. Actually, GPT-J itself was initially developed on Ray as well. You can find this page a concrete example of how to fine-tune GPT-J, right? So we just define a Hugging Face trainer on Ray, and you just feed your input data and fine-tune the model. So I'll actually later send a link to this example to the audience. So what rough performance can you expect? So actually, to make a fine-tune like even faster, you can use multiple nodes. But as you can see, we're using inexpensive GPU nodes, right? And then the cost is actually much lower than using the expensive A100 nodes. And yeah, you can like feed this data set of Shakespeare's to the model, and we can finish within 2 hours. And the cost is like $35. So similarly, we have an example of serving. It's very simple. If you, again, remember the Python example I gave in the beginning, the beauty of Ray is that everything is basically Python, right? It's very Python native. You just define how you want to generate the tokens. You define how you want to actually do inference on the model, and the different piece of the Python can do function calls with each other. Right, and you can define the resource requirements in this simple clause. So in conclusion, so we're seeing that people are using large language models in different ways, right? Calling the API is an in-house large language model. And our prediction is that the in-house large language models will become more and more common for many use cases because of the challenge of cost, latency, and data privacy. And meanwhile, the ecosystem is definitely still evolving for in-house large language models. And concretely, we see the ecosystem right now dividing into 2 cohorts or tech stacks. One is ultra performance, one is convenience and cheap. And Ray is playing a critical part in both parts, right? In the ultra high performance part, we're allowing advanced frameworks to do flexible sharding. In the convenient cheap part, we're allowing people to use really inexpensive GPUs and quickly iterate. So yeah, please consider Ray and AnyScale for your in-house large language model systems. And so just quickly also follow up with what Robert said. Resummit, here are some keynote speakers we have so far, including Cohere, OpenAI, LinkedIn, Uber, and Niantic. Please scan the QR code if you want to register. We have early bird now. And also, I want to come back to one question about the quantum computing. This is my favorite animation. So yeah, we haven't actually customized our algorithm with quantum, but what people can do is just to write Python code on your laptop, just define which part to run on quantum. And here you go. You send to the global data centers.
Any questions? I just wanted to add one more thing to what Zhang talked about. The LLM stack that he talked about, we actually released 3 blogs that talks about what's the role of Ray in building and challenges for in putting LLM models in production. The Alpa blog is there, and third, how you can actually use with deep fusion model. 3 blogs, go to any/blog, and you'll actually see it over there. Who's got the question? Somebody was here.
Can you talk a little bit more about multiple node serving? Like, how's that different from what is available outside? How does Ray does more there?
Yeah, sure. I think multiple node serving, as you can see from this example, is just becoming much easier. Just define how many replicas you want for your model. This is one thing. Another is, this is a simple case of one model, multiple nodes. So if you want more complicated cases, you can even define like multiple nodes, multiple models, how they chain with each other. This is called models assembly. It's just becoming much more Python native to define these correlations and number of replicas and the scaling behavior. Performance aspect, I think in terms of like one request, requesting one inference on the model, every framework is more or less the same, right? It's just a single node like application. I think the performance comes from one, how accurately you can like auto-scale, right? So in the simple case, we detect the CPU usage and the pending request. I think the performance edge, one very interesting aspect is when you do multiple models. And then I think Ray is really good at scaling the different parts separately. Right, so because in Ray, every unit is a process. For example, if you do it on Kubernetes, the unit is a pod, and you can only scale that pod like as a unit, which is sometimes much harder, and sometimes you are forced to make the decision to scale multiple models with the same scale, which is not ideal. Sure.
Any other questions?
Thank you. We heard that debugging the training LLM is very complicated because bugs come from everywhere. For example, hardware, or maybe your library or something. Can you talk a little bit about, is it easy to debug when we use Ray?
Yeah, I think this part is where, if you remember what Robert mentioned about the experience. Yeah, even though this slide itself is for any skill, but actually in open source Ray, where this is also a key area, monitoring and observability. So basically, we surface the error logs and other metrics from all the worker nodes. We try to summarize and we present on the dashboard and also the logs. We do smart things like deduplicate logs. This is an area we're developing really fast, very actively. And yeah, having the focused large language model use case will help the development, definitely. But I think one good thing about Ray is Python native. For example, from my past experience, before NSQ, I was at LinkedIn managing the Hadoop and Spark team. Like, if you cross the boundary between native and JVM, everything will become even more complicated. Yeah, I think Python native and Ray's execution model of turning RPC calls into function calls is helping in this regard.
I think one of the things that Ray really comes forth is we actually released a dashboard that allows you to provide you lenses that you can actually see exactly in real time what's happening. So you can find out how your memory is doing. You can find out how the tasks are being executed. You can find out how many GPUs are they using, how much RAM is used. If there's OEM errors, you can actually detect those things. And that's one of the greatest things about having these lenses into distributed computing. Distributed computing is not easy to debug, right? We are not at the stage where you can do step-by debugging in distributed computing. But these different lenses of observability gives you a good health and an eye and a spectrum of what's actually happening behind the distributed application you actually launched. And that's actually a great, great addition in Ray 2.4. Anything else? Oh, sorry. Here you go.
Hi. So one question on, you showed that when we are decorating the function, you could potentially specify the CPUs and GPUs to be used. If we don't specify that, is there any, like let's say if you have a farm of compute on both sides, would Ray auto-optimize the workload, let's say if my function has both characteristics?
Oh, yeah, this question is especially applicable to higher level libraries. Here, for simplicity, I'm introducing the low-level primitives for you to directly scale Python code. But this question is the most relevant when you use libraries, for example, read data. We have a library called read data set. What it does, for example, you read a large file from S3, you do certain operations like pre-processing and just UDF, and then we have the logic in the libraries to detect the actual workload and deciding the amount of resources. But of course, the actual heuristic and logic is something we're actively improving based on user feedback. So let me know if you want to try the early stage libraries as well.
I have one follow-up. Any scale, does it run on other clouds like Google and?
So right now we have AWS and
Okay.
GCP.
Got it.
Yeah.
Thank you. Have you done cost analysis of using, for instance, I don't know, OpenAI versus training and deploying yourself, like the full cost of training and deploying, to see when is it relevant to switch, like doing that kind of analysis of cost?
Let me repeat the question. Your question is, have we done cost analysis?
In the sense that some cases, for instance, let's say you want to fine-tune a model on a specific data set and do the analysis of, okay, how much does it cost me? If I want to have 100,000 requests a month, when is it more interesting to train?
Got it. So we haven't directly done this analysis, but I encourage you to look at this new model from Berkeley called Vicuna. They exactly did an analysis, I believe. Vicuna was also developed with the help of Ray at the distributed layer, but they did analysis of the model performance and the cost, right? Because you cannot talk about one. Huh?
Talking about economic cost.
Economic cost. Right. So I think we need to consider the model performance. Otherwise, it's not apple to apple. This is why I mentioned the Vicuna model. They did the analysis of the cost and model performance. They actually used GPT-4 to compare the performance of different models. Yes, it's public. Yeah. Kuna. Something like, yeah, so you can probably, I don't remember, yeah, exactly. So probably, yeah, so yeah, I can send you a link offline.